Hello everyone. So today we'll look into a problem where we are finding two elements with the sum nearest to zero, and this is the presentation that has two solutions, and we go over each of them to understand which one is a more feasible option to go with. So the problem that we have right now is there will be a list of integers that can be negative or positive, and we need to find two number pairs which when we add we'll get the closest to a zero. So there are a few assumptions that we can take into account. One is there will be positive as well as negative numbers in that list. The maximum, the sum of two elements that can happen is 10 to the power 9. So we will use this value later. And also there's a hint that we can sort it. So it will be easier to solve the problem. Other assumptions are the input will be in form of a list of integers. The output will be two integers, a pair from the same list. So for example, if we have input -4, 7, 6, 2, and -5, the final output should be -5 and 6, which is when summed is 1, which is the closest to 0 in present in this list. The first approach is a brute force approach where we will check each element in that list individually and we will find the pair and then we'll find the sum, and we need to iterate through the whole list twice with I and j pointer and see which pair is giving the least sum from it. So for this, the algorithm that we follow is we'll initialize a variable, we'll name it as min sum, and we'll store the sum that we have encountered, and we'll compare it if it's the least one or not. Then we'll have another variable which we'll call as result pair, where we'll store the elements whose sum are placed in the min sum so that we can return the result pair directly from the method. Third, we'll have to iterate in a nested loop, and there will be outer loop which will be indexed by I, and there will be inner loop that is indexed by j. And so to ensure that it is not doing any duplicate pairs, so we'll always maintain j is greater than I. Then for comparison, we'll use the current sum, which is the sum of the I and j present in the list. Then we'll compare the absolute value. And why absolute value? Because if we compare the absolute value and we find the least one, we do not need to bother about a negative or positive sign. Our aim is to find the least absolute value pair present in that input list. So when if we encounter some current sum which is less than the min sum, we'll update the min sum. Else we'll go ahead until we find the list from the available input, or we exhaust the list altogether. Also, we'll handle if we find 0, which is the exact match of our problem. If we find a pair that sums to 0, we'll directly return that pair. So the given input for the list that we saw, we'll get I and j, and the first iteration it will be picked up as -4 and 7, so the output is 3. So the in the code we'll see that 10 to the power 9 will be replaced by 3. So this is the least that we know of right now. In the next iteration it will be -4 and 6, and we'll see that it is 2, so it is lesser, it will get updated. Then it is 4 and 2, it is still 2, but since it is absolute it will match, so it's not the least, so we'll go to the next one. It will be 4 and 5, -9 won't update. Then it is 6 and -5 will give 1, which is the least, and this will be stored in the min sum. And after the whole list is exhausted, since this is the least pair that we found, -5 and 6 will be sent as an output and we'll get that result. Since we are traversing the whole list and there are two pointers, so we'll get a time complexity of n square. There will be so when we multiply n and n, we'll get n square. Then there's n, but since n square will be far greater than n, we'll ignore that, and the time complexity will be calculated as n square. So this is the sample script. We see that find closest to 0 brute force is the method that we've created. We'll pass the input array and then we'll get the length. If the length is less than 2, we'll return none. Why is this? This is actually handled as a edge case. We'll discuss the edge cases later. Minsum we have updated as a maximum value that can be possible. So with the first iteration itself, it will get updated to the first pair sum that we encounter. Then we have a result pair which are none right now. Iteration I have just added to show the difference between the two solutions that we are going to cover here. So right now it is initialized as 0. Then for the first loop, we give it as uh, go through all the n elements, and since we are starting with the first one and we are marking it as -1. For j, we are adding the starting point as the next element from I, and we'll traverse to the last one. Iteration we are updating as 1 since the first iteration loop is encountered. Then we get the current sum, which is the sum of I and j. Right now this will get updated because min sum right now is 10 to the power 9. So this will get updated and result pair will have the first pair like we saw in the previous example. This loop will continue until If we get something which is equal, in that case it will check without the absolute value. But if the absolute values are same, it will keep on checking until the list is exhausted, which means this loop is completed. Then we will get the result pair and the iteration. If we see the iteration for these problems, list inputs, we see that for the first one it took 10 iterations to find the answer. For the second one 10, for the third one 6, 6 and none. These 6 iteration are required because the number of elements in the input list are lesser, so that's why we get it with 6. But still, as the list increases, this iteration will increase at the factor of n square. So this is not a very fast approach, but it is a more simple one. Next we will see a two pointer approach. This is same data structure we are going to follow, and there are 2 pointers that are being set at the start and at the end of the list. So the algorithm that we will use needs to be worked upon on a sorted list. So sorting the list is the first important step. We are going to sort it in ascending order. Then we initialize the min sum similar to the first approach, but instead of I and j, we are having left pointer and right pointer here. So left pointer will be at the start of the list and right pointer will be at the end of the list. And since it is a sorted list, so left is pointing to the least uh, element in the list, and the right pointer is pointing to the highest or the biggest element in the list. When we iterate through the list, we will always maintain that left pointer is at a position less than the right pointer so that it doesn't cross over to the other side of the list. The calculation of current sum is similar, the summation of the elements that the both left and right pointer are pointing at. We compare the absolute value with a similar logic as previous, and the update logic for the current sum and min sum stays the same. What changes here is the decision step. Since we are not going to go through the whole thing or update the pointers on every iteration, what will follow is if the current sum that we have encountered is less than 0, which means the number is too small, we can go one level above, which means we can add a larger number. So we will move the left pointer because it is pointing to a lesser number. If the sum is more, it's the opposite, that we are having a very big number or too positive in this case. So we need something smaller. So we need to decrease the right side pointer. And if the sum is equal to 0, which means we have perfectly found the pair at whatever number of iteration may be. So we'll return the pair immediately. So for example, in iteration 1, it will be minus 5n plus 7. It is giving 2. So 2 is a big number and we need something smaller. So we can move the right pointer to one position on the left. So right now it is pointing to something smaller than 7. We do not know what it is right now, but we know it will be smaller than 7. So we got 6, we got 1, so this seems fine, and which is still greater than 0. So we can move one step more. We move to 2. Now it is minus 3, which is lesser than 0. So we need something bigger. So we move the left pointer to the next position, that is minus 4, and so we get minus 2. And it is going to go ahead in the similar manner. The time complexity for this is in two parts. One is the sorting, which we can take an example of merge sort, so it's n log n. And since we will find the perfect pair or the least pair in the one iteration itself, so the time complexity for scanning will be n. And when we add this, since n is negligible compared to n log n, we will take the time complexity as n log n. The code that we see here is we have a similar method. We are checking if the the input has more than two elements, and we sort it, and we initialize the left pointer and iteration. Right pointer is at the last element of the list. Min sum is the same, result pair is the same, and then as long as left pointer is less than the right pointer, we are in the iteration 1. We get the first sum, we compare the first sum. First sum will be obviously uh, lesser than the min sum, so this gets updated. If it is absolutely equal, then we check the non-absolute values, then result pair is updated if the condition is true. Decision step is, as we discussed, if the sum is lesser, we'll move the right pointer because we need something bigger. If the sum is more, we need something smaller, so we move the right pointer to one position on the left. If we find the exact sum, we get the perfect pair and we return it. So for the same example, we previously saw the iterations where 10, 10, and 6 and none for a one element list. For this approach, we see the iteration is 4, 4, 3, 3. So we get the output in 4 iteration itself. So it is much faster since it is only n log n time complexity is required for solution 2. Some of the edge cases are if there is one element no element, or if there are two elements, then for empty list we cannot check anything. But if there are two elements, there is nothing to compare with. We can directly run none. Right now we have an example where all are a mix of negative and positive numbers. But what happens if it is all positive and all negative? So we need something which is the smallest positive numbers or the largest negative numbers to find the closest to zero. And if there are duplicate elements, the first approach will take more time, but complexity is much better on solution 2. We just need it to be a sorted one. And also the space complexity, I've not included the iteration one because the iteration is completely optional and it is just to showcase what is the difference of iterations taken in the two solution. But apart from that, we have the space complexity listed here. And obviously the fastest and most more efficient one is the two pointer one. So this is the approach that we should take. So that's all for this one.